Hello, everyone, and welcome back to the Mechanochemistry Discussions. This seminar series is hosted by the NSF-funded Center for Mechanical Control of Chemistry, or the CMCC. I'm Ashley Martini. The goal of the seminar series is, as always, to bring the mechanochemistry community together. Our seminars stream live on the third Thursday of every month at 11 a.m. Eastern, and they're available to watch anytime on our YouTube channel. We've had an amazing group of seminar speakers over the past few years, and again, you can check them out anytime on the YouTube channel. We also have a great group planned for the upcoming months, and we hope that you will join us for future seminars. Before we get started, a few quick thank yous. Dr. James Batiste, the Center Director, Jennifer Belsick, the Center's Administrative Coordinator, and Dr. Frankie Antolon, the Center's Director of Outreach, and finally, Ryan Kwok, one of our CMCC students, without whom the seminar would not be possible. Please do continue to follow us, join us for future seminars, and keep track of us on the YouTube channel at CMCC Mechanochemistry Discussions. A few quick Q&A guidelines. This webinar is being recorded. If you have questions, we encourage you to email them to us at cmccdiscussions@gmail.com, or you can post them directly in the YouTube channel. Either way, they will be propagated to the speaker at the end of the presentation. Finally, we do want to hear from you. We would appreciate your input on how to improve the seminar series. You may either use the QR code shown here or the description of this webinar on the YouTube channel. Last but not least, it's my great pleasure to welcome today's seminar speaker, Dr. Mateusz Marianski, one of the CMCC's own. Professor Marianski has worked in academia in Poland, Germany, and the United States. After graduation from the University of Warsaw in Poland, he joined the group of Professor Donneberg at Hunter College City University of New York. He completed his PhD in 2013 and joined the group of Professors von Helden and Pagel at the Fritz Haber Institute of the Max Planck Society in Berlin to work on the development of molecular simulations of carbohydrates for gas phase glycoanalysis. In 2018, he returned to Hunter College, this time in the faculty ranks, where he established a research group in computational chemistry. Professor Marianski's research interests include structure-function relationships in carbohydrates, development of glycan-based receptors, and formation of chemical bonds under stress. Professor Marianski has been recognized with awards for outstanding scholarship at the City University of New York. It's my pleasure to welcome him for today's mechanochemistry discussions.
Okay, welcome everyone. My name is Mateusz Marianski, and I'm one of the investigators at the CMCC Center. And I would like to first of all thank you for giving me the opportunity to share my research here. So I'm going to talk about the prediction of mechanosusceptible reactions using mechanical distortions. So I would like to start very, very broadly. So asking a question, what is actually a chemical reaction? So to answer this question, I will do what my students will do it this day, and then just go to OpenAI and ask a question to generate me a picture of a chemical reaction. And this is what I would get. And this is a very interesting picture because on one hand, it shows a color change, which people would commonly associate with a chemical reaction, but it also implies two other things: solvents being present and vapors, which indicates heating. So essentially, what AI generated is the example of a solvothermal reaction, which involves heating of the reactants in the solvent bath to activate chemical transformation. And this is essentially what the chemical industry is doing. And because we have all the solvents that we require to heat and to run the chemical reactions, this requires a lot of materials, a lot of energy. And this is very difficult to reconcile with the principles of the green chemistry, such as preventing waste, improving the atom economy, or reducing derivatives. So what I want to talk today is whether mechanochemistry can offer an alternative solution to that in improving efficacy of chemical reactions. So let's go back to basics and look at the canonical example of an organic reaction. So we start from a substrate A and want to go to a product B. Of course, we know that in order to make this chemical transformation, we have to go through a transition state and activate the complex. and to pay a certain energy penalty to do that. So according to the transition state theory, the reaction rate can be related to the Boltzmann population of this activated complex, and we can provide heat in order to increase the population of that species. However, there's a lot of energy waste associated with that because we are activating multiple degrees of freedom in our system. So instead of a solvothermal activation, we can think about the directed push mechanochemical activation, where we go directly towards increasing towards the activated complex. This is, for instance, accounted by the Bell theory, where we have a force acting along the reaction coordinate. And this mechanochemical activation would benefit reactions with the increased yields, reduced weights, higher yields, and provide alternative selectivities. And systems like that have been realized. We are talking about the ball mill reactors or planetary mills on the laboratory scales, or a twin screw extruders that provides a constant product. And there have been theories developed to account for these chemical transformations, two main of them being the hotspot theory, and the second one being the surface area theory. The first one says that the increased reaction rates come from from colliding particles that creates hotspots of increased temperatures with accelerated rate. And the surface area theory says that by grinding, we increase the surface area, therefore increase the reaction rates. However, there are two critiques of this theory. First of all, the first one, hotspot theory, doesn't have a solid, convincing experimental evidence for the significance of this reaction of these hotspots. And the second one does not account for the fact that mechanochemical conditions might be changing the reaction trajectories. And there is a growing evidence showing that indeed mechanochemistry changes these reaction trajectories. My favorite example being the last example, where a mechanochemical conditions or the fluorination of the dibenzoyl methanes under mechanochemical conditions enable to avoid formation or usage of the calcium fluoride as the fluorination agent, and therefore reducing the environmental impact of the reaction while accessing a different selectivity of the products and allowing multiple fluorinations. So how do these changes to the reaction trajectory can manifest in mechanochemistry? So again, we start from the substrate, going to the product. If there is a change in the reaction kinetics, this has to be coming from the changes into the activation energy. So if we are able to understand how the external force changes the underlying reaction landscape, we should be able to predict the kinetics of the reaction. And vice versa is true if we understand what is the kinetics of the reaction, therefore we'll be able to access the underlying energy of activations. However, there are experimental limitations on how to measure these mechanochemical rates, which precludes understanding of the reaction kinetics. And the reason for that being is that the mechanochemical reactions are very often consist of several processes happening at the same time. And we can disentangle them to the so-called primary reactions, where we focus on the formation or the cleavage of the chemical bond, and the secondary reactions, all the rest, such as grinding and mixing of powders. So we discussed that in more details in the review in the RCS mechanochemistry last year. So the big question becomes how to disentangle these two processes such that we can access the kinetics of the reactions under mechanochemical condition, external force, and disentangle it from the secondary reactions. So for that, we focus on the test case pericyclic reaction of the Diels-Alder reaction, which is well understood reaction that has a negative volume activation, meaning that the reaction accelerates under pressure, and has been well studied both solvothermally and mechanochemically over the years. So we understand its temperature dependence, as well as mechanochemical force can alter the reaction selectivities and can alter the reaction selectivities. So in the first part of the talk, what I want to discuss is how to understand the acceleration of Diels-Alder reaction under uniaxial force through mechanical distortion. And in the second part of the talk, I'm going to focus on how to exploit this mechanical distortion to predict whether specific reaction is going to be mechanochemically susceptible or not. So The first problem that we have is that how to derive these most basic kinetic parameters, being force, time, and concentration in our experiments. So first, in this collaborative work between me, Ashley Martini's group, Rob Karpik, and Adam Braunschweig, we studied the Diels-Alder reaction to understand mechanochemical kinetics, to understand this how the specific parameters change the reaction. So this is our reaction set. So we use a parallel polymer pen lithography, which has been developed by Chad Merkin at Northwestern University, and the experiments has been done by Yerzhan and Zoldasov at ASRC in Adam's group. So we use this pen lithography to exert a force on the silica surface that has been functionalized with anthracene molecules as forming a monolayer, and then these this polymer pen lithography had inked that contained these dianophiles that were reacting with the anthracene under external force. So by setting up experiment like this, we have a certain advantages. First of all, monolayers of anthracene remove multiple particle effects, and then the piezo actuators provide a precise control of time and force at each spot of the reaction. So we use a tilted machine where this changes the amount of force that being exerted at the specific positions. So this enables a high throughput analysis in the parallel printing, and because of that, can determine the reaction rates as a function of force and time. And most importantly, these reactions are run under uniaxial stress, meaning that the force is acting from a very specific direction that we know, that we understand how it's in relation to the position of the anthracene molecule. So there is a series of control experiments and experimental details that I will not be discussing here. I refer to the paper there, but what I want to acknowledge here is that we have all these control experiments, and this is how the experimental outcome looks like, where we observe this fluorescent spots due to the fluorophore attached to the dye. So effectively, the experimental outcome would be a plate like this, where we can read the intensities of different spots as a function of time and force. And then starting from these intensities, we can derive a surface density of the reaction products, Diels-Alder adducts. And we can also understand what's the force acting, and this work has been done in Rob Karpik's group and his graduate student Li Yuan. So he did a lot of modeling and experimental work showing precisely what is the force acting at each of the spots, as well as what is the pressure, how it translates to the pressures there. So what we observe is this first order kinetics, where this is for one of the dienes, alkene, the simplest one, where we see that what is the intensity or the density of the product as a function of temperature and force, and we see that the reaction indeed accelerates under force. And this was true for all 4 dienes that we tried, and always the reaction rate increased with the applied force. So this could be summarized in the table like that, where we have a logarithm of the density of the anthracene, so decay of the substrate in this reaction, and we see that with the increasing pressures, the reaction rates being the slope of these curves increase. And this effect is different for each of the dienes, and we are seeing that for the alkene, the reaction rates from 0.16 megapascals to 0.32 megapascals increase 4 times. Similar effect is observed for the malachimide, but for instance, for the methacrylate, the reaction rates increased 40 times. So these could be all summarized in the Van Hoff equations like this. So where we relate the logarithm of the reaction rate to the logarithm of the pre-exponential factor minus energy of activation, Boltzmann constant times temperature, minus pressure, volume of activation, Boltzmann constant temperature. So we have a relation between the reaction rate and the pressure applied to the system. And if we plot all of these are going to the curves. And this is how the curve is going to look like. So what we see from here is what usually agrees with the Diels-Alder theory. So the energy of activations increases from methacrylate, which is the most electron withdrawing group on the diene, to the maleimide, most reactive species. But what we can also read from this plot is the volume of activation, which is being this delta V double dagger, being the slope of this curve. So we are seeing that the volume of activation decreases in this order, being the largest for the methacrylate. And if we calculate this volume of activations from these plots, what we are seeing and compare it to the volume of activations that are well known from the typical solvothermal reactions, we are seeing that the volume of activations are over 1,000 larger than under this uniaxial stress than under hydrostatic pressures that what has been reported usually. So this brings us to the next question. Why do we observe such a significant acceleration of the Diels-Alder reaction under uniaxial stress? So this work has been done by the graduate student in my lab, Herein. And the first question was, can we model this Diels-Alder reaction on the silica surface? So I will be discussing density functional theory calculations. All of these has been done on the usual level of theory that has been widely applied, M06XX, that has been widely applied to study Diels-Alder systems. So modeling transition states is not difficult. This is the transition state that we derive with the energy of activation being 82.8 kilojoules per mole. We simplified the silica surface as just as a small silica cluster to save some computational time and then focus on the reaction system as we have right now. So the question became, now, can we model the behavior of this transition state energy as a function of different degrees of freedom on the system? The assumption being that the external force, uniaxial force acting from the top, is going to bend specific angles that's going to modify the value of the transition state. So we started checking different angles one by one, starting from the silica carbon-carbon, where we bend the anthracene moiety, and then calculate the transition state energy as a function of this angle. So this is the change to the transition state energy. And what we are seeing here is that with respect to the relaxed transition state, it always increases. What I should note here is that we are both bending the same coordinate in the transition state complex as well as the reaction complex, So similarly, for the other angle that we checked, oxygen, silica, carbon, we saw the very similar effect. None of these is decreasing the activation energy. However, when we investigated this carbon-carbon-hydrogen angle, we saw that for free reagents, we are seeing the decrease of the activation energy, meaning that the reaction should be accelerated if we bend this carbon-carbon-hydrogen angle. So what is happening here is that if we bend this angle, and this hydrogen needs to be bent towards the diene. So when we bend it from the relaxed synchronous transition state, we are accessing this distorted asynchronous transition state that has been described in, for instance, this paper by Bickel-Kaut. This similar effect has been observed by Ashley, Martini, and Sergio in their paper published last year in Langmuir, where they still look at the system and they saw that indeed under higher pressure, there's a change in the conformational distribution of the carbon of these anthracene rings and a large bending of the carbon-carbon-hydrogen atom. These simulations have been done with the reactive force fields. So why is this carbon-carbon-hydrogen coordinate productive for our system? Obviously, if I'm distorting my transition state, I'm not going to lower the transition state energy because by definition, the transition state is the lowest point along the reaction coordinate, or the highest point along the reaction coordinate, but the lowest in every orthogonal direction to that. Therefore, I must be always increasing the energy, which is what happens here. Going from the black line to the blue line, I'm increasing the energy. But what we think is happening here is that we also bend the same coordinate in the reaction complex before the reaction. And this requires more energy than or the deformation requires more energy than the deformation of the transition state. So effectively, what we are seeing here is that under mild pressure, the deformation of the reagent complex is larger than the deformation of the transition state complex. Therefore, the overall transition reaction barrier decreases. And this can be shown in the equation like that, where we have our delta delta E as a change to the activation energy. And this is a different mechanism that what happens under hydrostatic pressure, where we have a direct decrease of the transition state energy, mostly associated for the fact that we are pushing the reagents together, also following the reaction coordinate. Here, what we have is we are bending this coordinate, which is an orthogonal coordinate to the reaction coordinate, and this forms this distorted complex and shifts the reaction towards a different trajectory. If we take a look at what has been published in the literature area, so for instance, the breaking bond of the organic mechanophores, we see that this principle is somehow similar principle in that. So by strategically placing weakened bond along these reaction coordinates, what we are doing here is that we are indeed weakening this pre-reaction complex, and this decreases the activation energy that allows breaking of the molecule. On one hand, this is a similar mechanism, but on the other hand, I want to note here that here it's a bond breakage, whereas what we are looking at is a covalent bond formation. So therefore, we are accessing this transition state from the opposite direction, and this is a completely different reaction trajectory. And since we published our paper, there has been some work that has been, using mechanical distortion to explain the unexpected rearrangement in the molecules, as well as there's an interesting work by Michael Baron showing a similar idea that we are pushing the reaction towards the parallel trajectory using an orthogonal direction that will accelerate the reaction, lower the reaction barriers. But what I would like to focus on the rest of the talk is trying to understand why this specific coordinate enhance the reaction rates and whether we can use this fact in predicting what other kind of reactions would be mechanosusceptible. So once again, what is happening here is that the energy of the distortion of the reaction complex must be larger than the energy of the distortion of the transition state, as encoded in this equation. And if we go back to the paper by Mikko, we see that in this distorted asynchronous transition state, the very reason what happens there is that by increasing the asynchronicity of this transition state, we are decreasing the Pauli repulsion in the system. This is in contrast to the reaction complex, because there, by bending the molecule, we are paying the same, if not larger, electron energy penalty to achieve the same effect. However, we do not get the stabilizing effect from the Pauli repulsion due to the presence of the diene being in the transition state complex. Therefore, this is what is responsible in our specific case for accelerating the reaction. So in other words, if we can find these examples where the distortion of the transition state requires less energy than the distortion of the reagent complex, these are going to be the cases with delta delta E being smaller than 0, and these are going to be types of the reactions that will be accelerated by mechanical distortion. So this brings us to the larger question: can we use this theory to predict mechanosusceptible reactions? And the question associated with that: what are the reaction classes that are mechanosusceptible? And what would be these productive mechanical distortions? What are the coordinates that we should be distorting in order to obtain the desired effect? This can be even narrowed down. Are there any specific stereoelectronic properties of the reagents that will enhance the reaction rates? And finally, can we translate all these findings to the experiment and to the actual reactions, where we can control the reaction trajectory by bending the molecule specifically and therefore obtain a desired product? So this project is possible due to the support of the CMCC, such that we can bring together experts from different fields that will work on the different aspects of the pipeline that we are designing. So on the beginning, we were interested in scanning a larger chemical space of different reactions. This is the work done by Diels-Alder's group at Texas A&M. We are interested in understanding how specific distortions change the reaction rates. And then we are also interested in validating our predictions. This is in collaboration with physical organic chemists, Adam Braunschweig at the ESRC at CUNY as well. So before I jump to my part, I would like to highlight Daniel's talk in April, where he discussed how he has been using AIMNet machine learning potentials to scan a large chemical space of over 2,000 Diels-Alder reactions divided in different reaction classes to identify which of these could be, in principle, mechanosusceptible. And what he's been doing is that he's looking at the Hessians of the reaction complex and the reactions and the reaction transition states. And by removing the reaction coordinate from these Hessians, he's projecting on the orthogonal directions to the reaction coordinate. He's trying to find what's the optimal direction of the force that would, in principle, lower the transition state. So, for instance, one highlight from his talk is this reaction over here, where by applying a specific force derived from the difference between these two Hessians, he's able to predict that this force is going to lower the transition state energy. And then by reoptimizing the system under explicit forces, he's able to indeed see that the energy drops by 2 kilocalories per mole. And this is mostly due to the fact that he's increasing the energy of the reagent, how we predicted that in the previous work. However, there is one problem with this work that always being brought up by the experimentalists is how do we translate this kind of a force to the experiment? We see that this comes from the Hessian. It's a highly complex deformation mode. So it's very difficult to think like, oh, how is it going to happen on the experimental scale? So this is the work that we are trying to focus on. So once again, we are starting from our solvothermal trajectory, and we are applying a force on the direction orthogonal to the reaction coordinate, trying to bring it to the new reaction and to the new mechanochemical trajectory. And being computational chemist, of course, the first way to think about any system is to use harmonic approximations. So we can recast this picture, this two-dimensional surface on the one-dimensional plot. So the blue line being solvothermal, this is our solvothermal reaction. And what we are trying to do is to push the reaction to the mechanochemical trajectory such that the energy of the reaction complex, distortion energy of the reaction complex is larger than the distortion energy of the transition state. And this requires that the force constant associated with this distortion must be larger than the force constant of the reaction complex. Then this is going to be a productive variable. So we can write it down as an equation such that this delta delta E, which is the change to the activation energy, due to the distortion along the direction orthogonal to the reaction coordinate, would be equal to the changes to the energy of the transition state, the distortion of the transition state, minus energy of the distortion of the reagent along these same trajectories, which under harmonic approximation can be expanded as a force squared divided by 2 force constants, so the difference between these two. And assuming that this force does not change during the reaction, this is going to be this simple equation where we have a force acting along this specific direction squared divided by 2, and then the difference between the reciprocals of the 2 force constants. So of course, there is a certain assumptions to this model. First of all, that we are saying that PES can be approximated by the harmonic function. And the second is that this orthogonal direction can be defined both in the reaction complex and the transition state. Also, I should note that we are removing here the direction that is parallel to the reaction trajectory. And we are focusing just on the pushing it to the parallel trajectory. So we can represent these changes by using harmonic approximations. So you can think about it that any molecules have a system of normal modes, and then we can, which is going to be by harmonic approximation, the orange dots on these plots. However, we can also deform the molecule using the same coordinate system, and then we can derive our numerical forces as well. And we can use the combination of normal modes, as we have here, to derive any desired distortion that in the system, and in the system just by rotation of our coordinate system. So this is initial idea that we have to approach this problem. However, what we realize very quickly is that we don't really need to access the Hessians here to get this normal modes, because we kind of can encode the distortion library and just derive the single points along the desired distortions by which we are going to get the forces acting from there. However, just to simplify the further calculations to predict the changes to the transition states, what we are actually doing now is the opposite thing, where we first derive the numerical forces and then try to fit the harmonic approximation to these numerical forces such that we get a very easy access to the force constants and and the forces along this direction. So let me explain a little bit more details what we get out of here. So here is one of the test reaction classes that Daniel was looking at, where we have a cyclopentadiene reacting with this diene file. And in this reaction class, we are going to put different groups at the A and X. This is the different reactions that we are looking at here. And all of these calculations, again, has been done at the DFT level of theory. So what we can get out of here is a matrix like that, where on one, in the columns, we have or in the rows, we have a different molecular distortions, being the bond-bond stretching, distortion of the specific angles, and distortion of the specific dihedrals. And in the columns, we have the reaction IDs, where different moieties at A and X are encoded in this table. So what we see here from this table is that most of the molecular distortions are not very productive. Or maybe I should say that what we encode in this table are these gamma parameters, which is this difference between the reciprocal constants as we define them here, just with the minus sign. So it's so we always get a positive number. Positive number indicates that there should be acceleration of the delta delta E is negative and the reaction should accelerate. So what we are seeing here is that most of these molecular distortions are not very productive. These are all bond stretchings, as well as angle deformations and some of the dihedral angle deformations. But we see that there are two specific coordinates, dihedral angle deformations, associated with BCC, carbon-carbon A, and Y, carbon-carbon X. And we see that if we bend these two angles, we can lower the transition state of these reactions. And this is very interesting observation. And also what we are seeing here is that if you look at this table carefully, some of these reactions are actually reactions between the same diene and dienophile, just in the different orientation leading to different stereoisomers. So we can look at these reactions now in pairs. And so for instance, here we have a reaction between the cyclopentadiene and two different arrangements of the diene, one being exo and one being endo with respect of this parafluorophenyl group here. And we see that one of these reactions is going to be much more mechanosusceptible than the other one. And this is not common because, for instance, here, where we have a sulfate group, these two gamma parameters are the same. Therefore, we expect that both reactions should accelerate, but we should not observe a change in the selectivity. And when we look at this is all observed in the transition state energies in the reactions for these reactions. So we see that the transition state energy of the purple arrangement drops faster than of the green arrangement. And then for the reaction 7 and 10, we see up to the large simulated forces, we don't see the change of the order of these activation energies. And we can translate these plots to predicted yields of the reactions, and we are seeing that under external applied force, we can expect at some point there will be a switch in the selectivity, going from complete reaction being completely selective towards the endoproduct, from endoproducts towards the exoproduct. And in the other case, we see that this requires a much larger forces, but to be honest, I believe that at this stage, our harmonic approximation just breaks down and we should not observe any switch. So now it brings another question. So why this reaction is mechanochemically sensitive, why the other one is not, and whether we can experimentally validate that. So we have two theories, or we have two mechanisms that could explain mechanosensitivity of some reactions. So the first one is that these deformations are going to lower the HOMO-LUMO gap in the system, which is essential for the Diels-Alder reaction. So again, these are our two reactions, these are the deformations, and we are seeing that the purple line drops faster than the green line. And if we look what happens with the LUMO orbital for this specific system, we see that there is going from the undistorted to a distorted state, there is a large rearrangement. And then what we are seeing for the purple dots, we see that there's a stabilization of the LUMO orbital and then drop in the energy gap between HOMO and LUMO orbitals. However, this does not always explain the the changes to the transition states. So for instance, in this pair of directions I already mentioned, we see that the energy of the LUMO orbitals is constant, and the gap actually increases with the deformation. So what we are thinking might be happening here is that by bending, we are changing now the electronic distribution along the system. We see a large change to the molecule charge on the carbon-carbon due to the bend of the red dots. And this is, for instance, an effect that we have not observed in the another reaction. So what I want to say here is that given that we have an access to the electronic structure to these reagents, we can now slowly, step by step, analyze what would be the stereochemical requirements and what are different mechanisms that bending of the molecule could accelerate the reactions. So now the question about the possible experimental validation of our finding, and this is ongoing work, but I think the most important step for this work is the proper selection of the targets. So what we've done is that we selected a set of different dienes and try in order to have them experience different effects, some of them being strongly mechanosensitive, some of them being not very sensitive to. So in the first case, we look what are the changes to the possible distribution of the products of these dienes to the reaction of the naphthalene, and we see that indeed one of the dienes might be very sensitive to force. We observe a switch in the product yields, but then some of them would not be sensitive or very little sensitive, most likely not. However, we also know that unfortunately naphthalene, because of the high energy barrier, is not a very good product, a very good molecule to look at experimentally. So we explored different options. So here is the d-phenylisobenzofurane, apparently a covalent chemical that you can just buy from Sigma Aldrich. And then we look at these reactions with different dienes, and we see that in some of the cases, the dark line is the expected yield, but then we also added the delta E, the activation energy, how it changes as a function of the force, due to this being important whether the reaction runs at all. So we see that some of these reactions are not going to be sensitive to the force, and then some other reactions with other dienes are going to be sensitive to external force, or just a little sensitive. And what is also interesting here is that we see that what the chemical outcome of the specific diene is going to be is changing between the reaction systems. So what we expected to be not as sensitive or mechanosusceptible diene in the case of the naphthalene, now we are seeing that it's going to have a strong mechanical response in the case of the d-phenylisobenzofurane, most likely due to the fact that now we have this bulky phenyl group that can interact with the diene. With the dienophile, sorry. And in the third case, we are looking at this furan functionalized with the electron withdrawing group. And here again, we are observing different effects, most of them being not sensitive to the force. So this is ongoing work right now to validate our experimental prediction. And I hope that in some time we'll be able to update you on this. And with this, I would like to wrap up my talk, move to the conclusions. So what I discussed today is that under mechanical conditions, we can activate thermally stored reactions as a result of the uniaxial force, of the uniaxial stress. And this occurrence of the mechanical force accelerating a reaction is possibly wider than previously anticipated. And what we also want to note is that this experimentally derived activation volumes are orders of magnitude larger than those that would be estimated from the transition state theory as a simple difference between the volume of the activated complex and the volume of the reagents in the system. And for the second part of the talk is that we are developing this computational pipeline to predict and understand mechanosusceptible reactions and then to validate the candidates. And this pipeline is working on using the idea of the mechanical distortions, creating mechanical distortions, activating or distorting the reagents such that the energy of the distortion is larger than the energy of the distortion of the transition state. And then the experimental verification of our work, as well as the formalizing the package to make it publicly available, is a work in progress. And with that, I want to thank you, the CMCC Center, and generous funding from the NSF and support for this work, with our grant to access our grant challenge of scaling up atomistic mechanochemical theory to enable predictive macroscale synthesis. And I also want to thank my other support, as well as my group, particularly Ryan Kwok, who has done most of the coding and most of the simulations that I presented here today. And with that, thank you very much for listening, and I'm happy to answer some questions.
Thank you, Marianski. Thank you very much for that excellent talk. We do have a few questions here. So first of all, when you're talking about calculating the activation volumes from the parallel pen-tip array experiments, can the value from each of those systems be connected in some way to the molecular volume changes at all, or the molecular movements being required for the transition?
Dr. Floyd, can I ask you to read the question slightly slower so I can gather them?
Yeah, no problem. Sorry. So when you calculate the activation volumes from the parallel pen-tip array experiments, can the value from each system be connected to the molecular volume changes or molecular movements required in the transition?
I must say, I do not really understand the question here. So if possible, I would suggest the author of this question to email me directly. So I'll be happy to answer that. Because here, like in this format, I would love to ask a clarification question. I must say, I do not understand it at this moment.
Okay, let me move to the next one. Instead of working from forces and distortion to reactions that were, and instead of working from the forces to figure out which reactions might work mechanochemically, could you work backwards and take a desired reaction to figure out what types of forces should be applied to make it more mechanochemically favorable?
Yeah, that's absolutely possible that we can start from the desired reaction and then understand how we should be distorting the molecule to accelerate this reaction. However, I also want to point out that this is the idea of the molecular distortions that we have here, that the library of different distortions, such that we can scan all the possible deformation of the molecule to find what would be possible most productive change, as well as understanding how different stereoelectronic effects and molecular structure affects it would also help us to predict or to suggest what are the possible changes to make it more mechanochemically active.
Okay. Okay. If a mechanochemical reaction in, say, a ball mill involves a liquid reagent, does this same analysis apply, or are we moving into a more solvothermal type system?
That's a very interesting question. So here, what we are working here is we are working on the molecules that do not have a chemical context. However, there is also a work from Daniel's group that how to relate the external force from the ball mill reactor to the molecular force in these reaction systems. So this is the first answer. The second answer regarding the lag itself. First is the question, what is the function of the lag? Whether it is solvating the system, moving to the solvothermal trajectories, or is it a changing specific properties of a
systems involved in the reaction, such as solvating cations or solvating nucleophiles. So in some cases where the lag is going to form will be a part of the reaction complex, not a solvent, but an active part of the reaction complex, we should be able to predict that the deformation of this reaction complex, or how the deformation of the reaction complex is changing the reaction kinetics as well.
Cool. Okay, next question. Does transition state theory apply to these reactions? If not, can we even use Bell theory? Do we need a descriptor different than activation volume?
It's a very good question. So what I would answer here is that first it's to wonder what is the activation volume at the first place. So it's the activation volume being defined as a difference between the volume of the transition state complex and the volume of each reagent. This is activation volume according to the transition state theory, whereas the activation volume can be also defined just as an empirical parameter, as we do in our experiment, which is the slope of this. Let's go back. Which is the slope of this curve here. And this might be the most appropriate definition of the activation volume at this time as just an empirical parameter. However, I must also note that if you read, for instance, a definition of the energy of activation, another parameter in this equation, it includes a caveat that the energy of activation might have a different meaning in computational chemistry. So maybe in terms of the computational chemistry, the activation volume might also have a little bit different definition, but I don't know what it might be at this moment.
I think this question probably follows a lot from that previous one, but can you comment more on the connection between the transition state theory activation volume versus the experimentally derived activation volumes? Is there some sort of key factor or parameter making transition state theory underestimate the activation volumes?
Well, the basic assumption, and this has been also alluded in the previous question, is that the transition state theory requires a Boltzmann population of the requires underlying Boltzmann population, and this is what is being accounted for in the solvothermal activation. We have this Boltzmann population over here. At the moment where we are applying external force, there is indeed, we might be moving away from the Boltzmann populations there, which means that the transition state theory might no longer be applicable, which also means that there might be some sort of underestimation. But again, this is going into weeds of the definition, of the formal definition, what the actually volume of activation might be on the atomistic level, whereas I think that on the empirical level, and this makes the overall definition of the activation volume a little bit more difficult than what would be, for instance, the empirical definition as just the slope of the curve.
I think that's all our questions. So thank you very much for your time. It was a pleasure to have your talk today.
It was a pleasure. Thank you very much for listening, and thank you very much for interesting questions.
Thank you, Professor Marianski, for that outstanding presentation. And thank you so much for joining us. Just a reminder that all of our amazing seminar speakers are available to watch anytime on the CMCC Mechanochemistry Discussions YouTube channel. We also do welcome your input for how to improve the seminar series, and you can provide that input via survey with the QR code shown here or via the link in the description of this webinar. Last but not least, please do join us for the upcoming seminars as part of this outstanding seminar series. Thank you again for joining us.